Let's take a look at multidimensional Newton's method and how it compares to using steepest descent. So a lot of this code is the same as I've shown before. I'm going to use a different objective function this time than we've used before. I'm going to use a logistic, kind of a logistic regression data set that I made up here. If you just look at the left half, it's a fairly straightforward logistic regression where we have kind of more low values to begin with and then more high values, but it's not perfectly separable. And then the same thing over here. And so the question is, if I just had this data, here would be the optimal curve for it if I just had the data on the left half. If I just had the data on the right half, the optimal curve would be like that. Pretty much the same thing, just moved over. And so what will the optimal curve be? Is it better to like stick to this curve and just massively mispredict these points, or vice versa? Or will the best curve kind of go through the middle somehow? And is this curve like a local optimum, and this a curve over here would be a local optimum, and would a curve in the center be like kind of the top of a mountain pass between two local minima? So we'll see. So we're going to set up our logistic loss regression function. This takes a lot of care because if you end up with large values, the e to a power can overflow. So I got this code from a website that takes a lot of care to avoid overflows and underflows. But you don't have to worry about all that. Here we're computing the true optimum objective function value. We did that by calling the stats models package that does logistic regression and got the true optimal coefficients, and then we're asking what's the loss function, the objective function at those coefficients. Ooh. All right, then we have the same code we had before for finding a bracket, and we tested a little bit. Same code we had before for golden section. Yeah, we tested a little bit just like we did before. And then last time we had finite difference derivative or gradient. So that's all the same as before, but now I'm going to use finite difference Hessians, and notice the similarity. So here I'm taking the approach of saying the Hessian tells us about the change in the gradient. So instead of computing each cell of the Hessian by itself, like having a double for loop, one for the rows, one for the columns, I'm just doing a single for loop, computing the gradient at slightly different positions and then talking about the change in the gradient here. So this function actually has a structure very similar to the gradient code. It's just that instead of getting a single function value and then computing the change, I get the gradient value and then compute the change. So that's a nice parallelism. It's also interesting to compute the angle between each step, so I have code here that does that. We did that before. Now let's take a look at something interesting. Since we'll be computing the Hessian by finite differences, let's test it out and see if it works. I have a quadratic objective function here, and it's this quadratic, so I know exactly what the Hessian should be. It should be basically 2 times that in one entry, 2 times that in another entry, and 2 times that, but split across the two diagonal and off-diagonal elements. And the Hessian should be the same no matter where I evaluate the objective function. So here I'm trying it at the origin and at some combination of numbers I just made up. And is the Hessian basically the same at the origin and at that combination when I do it by finite differences? It's not exactly the same, but I'd say it's close enough. So that also helps me know that my Hessian code is working. Here I'm just doing the gradient using a few different delta x values and seeing that I should get basically the same thing. But now let's test the Hessian at different delta x values. We've seen arguments before that 10 to the negative 7th is best for computing finite difference derivatives, but the Hessian is a second derivative, so it's worth a little bit of investigation. So here I'm computing the Hessian for the same quadratic at 10 to the negative 0 for delta x, 10 to the negative 1, 10 to the negative 2, and you can see that it's exactly right, at least to whatever rounding precision. Here it's still pretty much right. Here it's still pretty much right. Now we're getting, the round off is kind of sneaking closer to the beginning, and then at 10 to the negative 8th, it is very far wrong. That means for the Hessian we should use like 10 to the negative 6, maybe 10 to the negative 5, just to stay safe. And then we do the same thing for the Hessian of the logistic regression. And we can see that it's pretty much the same at 10 to the negative 2, 10 to the negative 3, 10 to the negative 4, 10 to the negative 5 is all about basically the same. 10 to the negative 6 is still pretty much the same. But then at 10 to the negative 7, you're seeing some difference here, 0.19 versus 0.18. And then at 10 to the negative 8, it is just way wrong. So again, probably more like 10 to the negative 5, just to be safe. All right, here's our steepest descent. Same basic code as before. I changed just a little bit of the output. Instead of returning a bunch of individual history arrays, I put them all together into something called a Python dictionary. So that makes it easier to store it all at once and say, this was what happened with steepest descent. All right, and then here's the Newton's method. Let's take a look at steepest descent real quick. Here we get the gradient, and then we make up a function, a one-dimensional search function using the gradient. In the Newton's method, we get the gradient, we get the Hessian, and then we make the search direction by saying invert the Hessian and multiply by the gradient. I know I said that really we should solve a system with the Hessian and the gradient rather than inverting it, but this is just a two-dimensional example, so the speed difference is totally negligible. And then now we're using the search direction we computed rather than the gradient as the search direction. All right, and then we output some stuff for debugging, and here's where we actually take the step once we figured out the new alpha from the bracket and golden section. All right, and then just trying out the objective function just to make sure everything works. So now we've seen all the setup, and in the next video we'll actually look at what happened during the optimization.